At our last lecture, we looked at how molarity tells you the difference between these two scenarios. You don't have to write anything yet, but we looked at calculating molarity is basically a special way of counting the particles. This guy here would have a low molarity because he's so dilute. This guy here would have a higher molarity because he's so concentrated. Again, dilute, not very many particles dissolved when compared to the amount of solvent you have. Concentrated, a lot of particles dissolved in regard to the amount of solvent that you have. In order to make one become the other, though, if I had this guy that was like 18 molar, all right, well, depending on what it is, 18 molar is a very high molarity. That's a very dangerous liquid in cases where it contains particles that have any capacity of being dangerous. And then, instead of messing with 18 molar, if we wanted to make it 2 molar, things that are more common that I would use in the lab with you, we need a way to change one into the other. And the way that we do that is dilution. All right. Now that connects to our vocab word we already have. If I want to make the concentrated guy look more like the diluted guy, I would go through the process of dilution. What do you think I need to do to this beaker in order to make him look like that? What would I add to him? Not heat. Water. More solvent. If I poured him into a much bigger beaker and started dumping water in it, these particles would start to spread out to the point where it could look like that at any given place. When you dilute, you're basically taking a solution with a high molarity, adding more solvents to it in order to dilute it, which is going to drop the molarity. The equation that we use to dilute is this guy here. I'll be giving you the equation on the test. You just need to know how to use it. But let's talk about what its parts are. Let's leave that picture up, actually. This is molarity 1, volume 1 equals molarity 2, volume 2 is what it stands for. And it's going from one beaker to the other. Now, I have these swapped, which probably isn't great for your eyes, but follow me. Remember, the whole point of diluting is to make this look like this. So if I had a starting molarity, I gave you 18 molar, and a starting volume, let's say that there was 100 milliliters in there. All right, this would be my M1, my first molarity that I start with, and my V1, my volume that I start with. And I can run a calculation here to figure out exactly how much water to add to make it a different molarity, the second, the ending, the final molarity, and we said 2 molar, for example, would be something that I would give you in lab. And we could figure out, well, how many liters of water do we need this guy to contain to make this happen? All right, again, you shouldn't be writing. We're going to do a real problem in a second. But this would be my molarity 1 and my volume 1, just describing my starting beaker. And then my ending molarity that I desire was 2, and we could pop those numbers in. It just becomes an algebra equation to figure out what my ending volume would be. Now, if any of those errors confuse you, don't worry. This isn't how we solve it. This is a conceptual look at what we're about to do. This will be the first problem. Pause the video, write it down. It says, what is the molarity of a solution that is made by diluting 60 mils of a 2.75 molar solution of hydrochloric acid to 350 mils? Now, I could draw a picture of exactly what it just referred to. We're always going to have a beaker with particles dissolved in it, and it's going to give you a description of that beaker. The big phrase that you look for in regards to finding your ones, the stuff you're starting with, is of A. You see the of A there, right here? The of A is usually the ones that will connect those two together. And here's what it says. In this beaker, there's 60 milliliters of liquid in there. All right, so if it was graduated, it would be up to the 60 milliliter mark. And its molarity is 2.75 milliliters. I'm sorry, molar. Just bad units. All right. This wants to know what happens if I raise up the amount of solvent. Instead of there being only 60 mils, what if we poured in water until there was 350 mils? That would make the water level go way up. It's going to stretch those particles out and make the molarity drop. Now, we don't know what the molarity is yet, but we can plug and chug pretty simply. So there's my equation. Here we go. My first molarity is 2.75. All right, of course, these are multiplying against each other. Two variables up against one another multiply. All right, I want to give myself more space. All right, times my starting volume, which was 60 milliliters. Now make sure you know your units. All right, we've been doing this a long time. But units of volume, all right, is milliliters, liters, kiloliters. So my starting volume is 60. All right, so M1 V1 equals, now down to what it's going to become when we add more water. We don't know what the molarity is yet, so what letter do y'all want to use for our unknown? A lot of people like X. We're solving for him. But my ending volume was 350 milliliters. That's the amount of liquid that was in there after we added a bunch of water to dilute it. And hopefully from here, you can see how to simplify this. Let's multiply the left first. 2.75 times 60. I get 165 on the left. What's x times 350? 350x. Yay for algebra. How do you solve for x? Do the opposite of whatever he's doing. Right now, x is in a multiplying situation. The opposite of multiplying is divided. So if you divide 350, that'll get x by himself. Whatever you do to one side of an equality, you must do to the other. And that will give you your answer. What'd you get? Sorry? 0.4, sorry. There he is. So again, make sure you see what's happening chemically, though. What we started with was 2.75 molar, which isn't real dangerous. But by adding all this water to it, up to 350, now it's really not dangerous. All right, it made the molarity drop, which is what dilution will always do. All right, the M2, the ending molarity, will always be smaller than the M1. That's the whole point of the process. Let's do another one. Problem 2. To what volume should 6.5 milliliters of a 4 molar acetic acid solution be diluted in order to obtain a final solution that's 1.5 molar? Like always, we'll pull the numbers out. I'm going to keep drawing the pictures. Drawing the pictures is not a part of anything you have to do. I just like you to be able to visualize what this is actually talking about. I use this equation more than any other equation doing what I do here at Madison. So I like M1V1 equals M2V2. All right? So again, this is the same beaker. This is like a before and after of the same beaker. All right? There's always going to be less water in the 1 than there is in the 2. All right, so we're going to be adding water to make this happen. This says, what's the key phrase for building the beaker? Of A. Find the phrase of A. And those will be the two numbers you're worried about. This first beaker is 6.5 mils. Right, so 6.5 milliliters, that's how much water's in there. And the molarity is 4. That's how strong it is. All right, in regard to the particles that are in there, it's 4 molar. This scientist wants to change this beaker into a safer molarity of 1.5 molar. All right, well, the only way to make the molarity drop is to make the water level rise. By dumping in water, it'll make it safer to use. This wants to know, to make that happen, how much water must there be in there? M1B1 equals M2B2. My starting molarity was 4. My starting volume was 6.5. My ending molarity will be 1.5 when we're all done with it. So how much water is in there? Finish it. Find an answer. Let's simplify the left first. 4 times 6.5 is 26. 1.5 times x is, divide by the number connected to the x. Divide by 1.5 on both sides. What did you get for the final amount of water over here? 17 point what? 17.3. So there you go. In order to make this acetic acid solution turn from a molarity of 4 to a molarity of 1.5, you'd have to add water. Hey, look up here. Listen to this question. How much water did they have to add to make that happen? How much water? .8 grams. Look, there's another way to look at this here. Understand that this beaker only had 6.5 milliliters when we started and 17.3 milliliters when we ended. But what I just asked is, well, then how much H2O was dumped in there in order to make that true? And the answer is 10.8 mils, which is the difference from here to here. In order to make that 6.5 mils, you'd have to dump in this much, and then you'd have that much. That's a very important distinction because there's another type of problem that we're about to look at. What I did here is I added water. And you see this blue word I just wrote? That guy right there? He's a key word in some of these problems. Let me show you what I mean. One of the reasons I like to draw pictures the whole time is because this other type of problem, you can really see it if you're drawing the beakers and looking at what's actually happening. But do you see the phrase adding? In a dilutions problem, in the first two that we looked at, the word add, adding, or added wasn't there. Sometimes it is there, in which case it's giving you a scenario that it wants you to just be able to chemically decipher. So let's draw our picture again, based off the wording of this problem. Do you see the phrase of A? Do you see it? Find of A. Remember, it's connecting the two numbers that will build the beaker. The only place I see that phrase is in between the 65 and the 9.7. So, my starting beaker here, with just a little bit of solvent in it, has 65 mils of solvent and a molarity of 9.7 molar. Now, that's a really strong molarity. If that's acid, Does it say what this is? No. If that's acid, that's send you to the hospital acid. All right. So let's make it safer. But instead of just giving you the amount of water that it's going to have when it's over, it gives you the amount of water that's going to be added to that beaker. How much water is being added? 100 mils. So here's what you got to do, guys. When you're doing a dilutions problem, when you start the problem, scan your eyes for the word, the phrase, add, adding, or added. If it's not there, then just build your beakers and use the equation. If it is there, then realize that they're not giving you a final volume. What is the final volume? 165 mils. You had to do something to get that. You had to add. Because if I have 65 mils and I pour 100 more mils in there, now I have 165 mils. So now my water level's way up there. And now we can solve for the molarity. See if you can get that molarity. My starting molarity was 9.7. My starting volume was 65. My ending molarity is what we're trying to find out. And after I added my 100 mils to my beaker, my ending volume was 165. 9.7 times 65 is 630.5. $165 times x is 165x. Stop me if anything doesn't match your work. Divide by the number connected to the x. Did you get 3.82? Now, even this molarity is still kind of high in regards to something I would give students. So what could I do to make that molarity go even lower? Just keep adding water. Keep adding water, molarity keeps dropping. What do y'all think about dilutions? You try one.
Hi. This is our last problem.
All right, let's build a beaker. I see my phrase of A telling me exactly what we're starting with here with my little bit of solvent. All right, we've got 2.5 liters in there with a very strong molarity, and it's giving us sulfuric acid, so it's one of the strongest acids that there are. So this is a very serious sample of solution here. All right. It wants to know, I see the word add, ding, add the word add, that's a big deal. I'm going to add some water to this very dangerous solution, 27.5 liters. All right, so that's a whole bunch of water they're dumping in there. Let's see what that does to our sample. Well, it's going to make the water rise. Of course, how much water is going to be in there now? 30 liters. All right, because this plus this is 30. All right, so what will that do to the molarity? Well, let's find out. My starting molarity was 12. My starting volume was 2.5. My ending molarity is what we're going to find. And my ending volume was 30 liters. Now, of course, what the most obvious mistake that students make is they'll find a place for this number to go into the equation somewhere. All right? That's why you've got to look for add, adding, or added right away. Because if you find a reason to put 27.5 into any of those spots, then you're done. So be careful. 12 times 2.5 is 30. Is that right? I guess that makes sense. 30 times x is 30x. Divide by the number connected to the x. And what's 30 divided by 30? Look at that. Now it's safe to use. I would happily give you 1 molar sulfuric acid. And now there's a bunch of it. That's the other good thing about diluting, is not only is that solution safe now, but there's a ton of it because I added so much water. Any questions?